Hello, everyone. Thanks again. My name is Danielle Cook, and I am an aerospace engineer in the acoustics branch at the NASA Glenn Research Center. And today I'm very happy to be representing a great team of inventors and researchers at NASA who are working on a bio-inspired acoustic absorber. This is technology that we hope can be used to make the world quieter. So thanks for joining us this afternoon. I know we have a diverse audience with us today, and to help guide our attention, I've prepared a roadmap for my presentation. I'd like to begin with a visual abstract. That was a concept that I learned in a workshop not too long ago. It's one slide at the beginning that I tried to create to help convey our main ideas visually. Then I want to unpack that by considering our motivation for this research. I want to define the broad problem and the consequences of noise pollution. And hopefully this will help us think of the many ways that this technology could be put to use. I would like to describe our concept, the bio-inspired broadband acoustic absorber, a little bit. We are maturing this technology for aviation use at NASA, and I can describe our prototype development and the research that's in progress. We have many test rigs and facilities available for acoustic testing at NASA, and I can give you a few details about those too. I'll leave you with some selected publications and presentations that you can look up on your own to find out more. We've also prepared some educational outreach materials for students and educators in the audience. I'd like to conclude with an executive summary to acknowledge our team and supporters, and then turn the floor back over to Renee for some information about the Tech Transfer Office, and then I'll take some questions. So first, our visual abstract. At NASA, we've been motivated to reduce aircraft engine noise pollution, and we've been inspired by the acoustic absorption of bundles of natural reeds. And as a result of our curiosity and some efforts, NASA has patented a bio-inspired broadband acoustic absorber. It's a mouthful, so we call it the BioLiner for short. Proof of concept tests at NASA have shown that synthetic structures that resemble bundles of natural reeds offer an increase in sound absorption at frequencies below 1,000 hertz as compared to state-of-the-art commercially available structures of similar thicknesses, weights, and volumes. And we believe that the BioLiner can be developed for many automotive, marine, industrial, and architectural noise control applications. So let's back up a little bit more and to think about what motivated this work in the first place. And it really does come down to a common question. Where can you go to get a little peace and quiet in this world? Where can you go to get a little peace and quiet to sleep? We all ask this question whether we're trying to get some rest in a house or an apartment, inside an aircraft, or even a spacecraft. Shown here on the right is astronaut Scott Kelly's sleeping quarters for the year that he spent in space on board the International Space Station. Where can you go to get a little peace and quiet to learn? Finding a place that you can think without distracting noises is important, whether you're trying to learn in your home, in a classroom, in a gymnasium, whether you're playing basketball or some other sport, or if you're in the school band or orchestra. Auditoriums are big multi-purpose spaces used for assemblies and all sorts of special events, each with their own acoustic characteristics. And speech intelligibility is often a concern in these spaces. Or what about peace and quiet at work? Do you work in a factory, outdoors, in an industrial setting with noisy tools, or in a musical setting? Speaking for myself and also as a parent, I know that not all sounds that an instrument makes can be considered music. It takes time and practice to learn how to play a musical instrument. And although musicians make sounds, they're also concerned about reducing the extraneous noises in the environment during recording sessions too. Musicians also often practice in small rooms. And what about all those home studios we've all cobbled together during this crazy pandemic for all our virtual meetings and classes? And where do you go to get peace and quiet when it's time to take a break? If you're inside, do you go outside onto a balcony or a patio or a backyard? Do you go into a park in your city or neighborhood? What's the soundscapes like in those places? We don't often think about finding peace and quiet when we want to go out with friends to a restaurant, but The experience is different whether you're going out occasionally or for an evening, or whether you're an employee working in that environment for days and weeks on end. So I just want to encourage you to think about the soundscapes in your life. In fact, whether you live and work in a rural community, a suburb, a city, or a space station, noise isn't just a nuisance. We know that noise is also a widespread health, safety, and environmental problem. So what is noise? Basically, noise is unwanted sound, and therefore noise is subjective. It depends on what you like to hear and what you don't like to hear. Exposure to loud sounds, especially for long durations, can damage your hearing, whether you wanted to hear that sound or not. The Center for Disease Control tells us that hearing loss is the third most common chronic physical condition in the United States, and it's more prevalent than diabetes or cancer. So it's affecting a lot of people. And while we're adding numbers to the discussion, here are a few notes about hearing and sound. To start, we hear sounds of different frequencies, just like we see light of different colors. Humans can hear sounds ranging from about 20 hertz to 20 kilohertz in frequency. Infrasound is generally considered sound below the lower threshold of human hearing, so sounds below 20 hertz. And ultrasound is the opposite. Sounds above our upper limit of hearing, sounds above 20 kilohertz. And clearly animals have different hearing capacities as shown in this graph of data by Dr. Richard Fay and his colleagues. These are biologists who study the hearing capabilities of vertebrates. And each animal in that graph hears sound over a different frequency range. Some have a very broad hearing range and some have a very narrow hearing range. And I can only imagine the kind of experiments they perform to determine all that. Human hearing is most sensitive around 1,000 hertz, and that's one reason why we're studying sounds and sound absorption from 400 to 3,000 hertz in our tests. From the National Institute of Occupational Safety and Health, we learned that occupational hearing loss is one of the most common work-related injuries in the United States. Approximately 22 million US workers are exposed to hazardous noise levels at work. And this is an expensive problem. An estimated $242 million is spent annually on workers' compensation for hearing loss disability. To protect human hearing, NIOSH recommends removing the hazardous noise from the workplace whenever possible, and then using hearing protectors, especially in those situations where you might be exposed to loud sounds over a long period of time. The National Park Service does have their own perspective on this, as they remind us in recent publications and presentations at internoise conferences. That pervasive flight traffic, coupled with an extensive road network, eliminates natural quiet across most of the United States. In the US, only about 12% of the country has an impact of 1.4 dBA or less. And the plot I'm showing here on the right is a map from the National Park Service estimating, modeling the existing soundscape in the United States, taking into account our transportation systems. You can see that where there's light, there's sound. We use artificial lights to illuminate our traffic corridors in our cities, which are coincidentally the loudest places in the United States. Louder conditions are shown in yellow and quieter conditions are shown in blue in this map. So basically, if you're living in a place where you cannot see the Milky Way at night, you probably can't hear the quietest sounds of nature either. We can contrast those estimates to the natural conditions in the United States that would exist if we weren't hearing so much transportation noise. In this map, the quieter sounds are shown in the yellows and the oranges in the more arid regions of the United States, and the louder areas are shown in blues and greens. And those are places where there's plants and animals and water and waves and wind. Uh, we already know the solution to noise pollution. We just need to turn off all the machines we use every day at the same time. And if we could ever do that, we would restore pristine natural sound conditions instantaneously. You know, we don't have to sweep up noise pollution like you might have to sweep up solid waste or air pollution. But in doing so, by turning off all our machines at the same time, we would be giving up the benefits of those machines. We are now a society that's now completely dependent upon technology for survival. We clearly want to have the benefits of those machines without the penalties of pollution. The US Department of Transportation also provides some information about transportation noise. You can get online and explore the soundscape in your neighborhood using the interactive Noise Transportation Noise Map. National Transportation Noise Map. The noise map I've shown here is near the Hampton, Virginia area where NASA Langley is located. You can see areas near the airports where the airplanes are dominant sources of noise pollution. We have made significant progress since the 1960s. Individual aircraft are much quieter, but we sort of counteracted that by tripling the number of vehicles operating on land, sea, and air over that same period of time. The International Civil Aviation Organization, ICAO, recommends that we take a look at 4 different approaches when it comes to reducing aviation noise pollution. By first identifying and reducing noise sources, the airplanes themselves, then going on to carefully use the land around the airports to protect the quality of life for people living nearby. We can also use the aircraft operational procedures to reduce takeoff and landing noise, and as a last resort, using restrictions or curfews to limit the number of flights. Commercial aircraft noise is regulated, and those regulations help us to create the conditions of international competition and collaboration. Quiet aircraft do have a competitive advantage in the global market, and noise is often a barrier for creating new airports. So what's NASA doing about all this? NASA research teams are working hard today, and we're thinking into the future too. We're asking a challenging question. How might we develop a commercial air transportation system that's accessible to a growing population, that's cleaner and safer and quieter than the one we have today? On the right are a few of the concept aircraft that are guiding our collective imagination as we go about trying to change the airframes, change the engines, change how the engines are integrated into those airframes so that we can fly more sustainably with machines. Even though researchers at NASA are hard at work developing technology for aviation and aerospace purposes, the Tech Transfer Office is asking us to think more broadly. We're wondering, and we're inviting others to consider, can technology patented by NASA be developed into a wider range of industrial, automotive, marine, architectural products beyond aerospace use? In our case, we're suggesting that our technology might be useful as a variety of commercial noise control products. And we know this kind of story is true. There are thousands of examples, inspiration for us really, that are cataloged in the NASA spin-off websites and publications. So let's narrow our focus even more. If we're going to significantly reduce noise pollution, we're going to need to make airplanes quieter. And how do we make an aircraft quieter? It's a huge machine with thousands of parts. We do need to focus on the engine, we know that. The acoustics branch at NASA Glenn, where I work, has been performing aerodynamic and acoustic research for aircraft engines since the 1940s. We know that we will need to continue to integrate acoustically absorbent liners into aircraft engines and fuselages of all types for the foreseeable future. Acoustic liners are already installed in turbofan engines today. So there's homework for you. The next time you get into an airplane, as you're boarding, you can take a look into the engine. If you have a turbofan, you might look upstream of the fan, and you can often see that the duct section is perforated. That's an acoustic liner, and it's there for a purpose. That liner is to absorb sounds generated on the inside of the engine from all the rotating parts and the air rushing through before that sound, those unwanted sound escape through the engine inlet and propagates to the ground where it's perceived as noise pollution. If you could see underneath the perforated surface of today's aircraft engine liners, you might see one or more layers of honeycomb. Preferred over honeycomb acoustic liners are structures that use resonance to absorb sound during flight. These kind of structures are also manufacturable, they're durable, they're capable of surviving the engine operating conditions, and they're really a hard act to follow. Preferred over honeycomb structures have been used in aircraft engines for over 50 years. Now, melamine foam is another type of commercially available acoustic absorber on the market today, and it's probably one of the most popular. I'm showing a piece of melamine that was used as a baseline in our test at the bottom of the slide. This lightweight porous foam is great at absorbing sound. Unfortunately, it's also great at absorbing water and oil, which does impact its acoustic performance. Melamine is also not durable enough for use inside an aircraft engine either. And while both of these styles of acoustic absorbers are impressive, neither are perfect. They're not infinitely thin, they're not free. We joke in the acoustics branch that we're looking for magical noise reducing paint, something that would be very thin, easy to apply, that absorbs sound at all frequencies. More realistically, though, we're looking for improved structures to be used as aircraft engine acoustic liners. The first proof of concept data for the bioliner was acquired in the NASA Glenn and NASA Langley normal incidence impedance tubes. These devices are fairly straightforward benchtop rigs, though it's always challenging to perform accurate standardized acoustic measurements. In these tests, you put a material sample shown here on the right at the end of a long tube with a speaker on the other end. Pairs of microphones record the sound pressures inside the tube, and from these sound pressure measurements, you can calculate what sound is incident, what sound is reflected, so you can determine what sound was absorbed by your material. So what did we measure for these baseline acoustic liners? On the right is a graph of acoustic absorption coefficient versus frequency from the test of the baseline absorbers in the normal incidence impedance tube that I just showed you. As you can see, above 1,000 hertz, both absorbers perform really well, absorbing almost all the sound. Below 1,000 hertz, these liners absorb less. In this test, a material that absorbs all sound would have an acoustic absorption coefficient equal to 1, and a material that does not absorb any sound at all would have an acoustic absorption coefficient equal to 0. So where does that leave us? Our team turned to nature and was inspired by the acoustic absorption of bundles of natural reeds, tall grasses that grow in wetlands across the world. People have been using natural reeds for millennia, for housing, for irrigation and control of waterways, flooring, and for art and music. We first learned about this when we read about experiments performed at the University of Liverpool. Dr. David Oldham and his colleagues were studying materials for sustainable road noise barriers, and they were measuring the acoustic absorption of natural reeds in several different orientations relative to the incoming sound. We were inspired by how thin, in that case about 2 inches in thickness, bundles of natural reeds in the transverse orientation were seemingly good at absorbing sound below 1,000 hertz. That inspiration led us to design and 3D print plastic prototypes that resembled the natural reeds, because natural reeds wouldn't survive the harsh conditions inside an aircraft engines. And for that matter, these first prototypes um, probably are in the same boat, that we're looking for durable things. But some of the first prototypes that we made were loose plastic reeds shown here in gray. And the gray ones were packed into a retainer to hold them together. And some of the prototypes that we made featured reeds that were fixed in place, and we did that with a printed base plate. And the fixed prototypes don't need a retainer to hold their shape. So let's compare. We can take a look at our baselines again, and we can see that the melamine and the double degree of freedom liners impressively absorb sound above 1,000 hertz, but there's room for improvement below 1,000 hertz. And this is quite intriguing because the pores are distributed so very differently in these two samples. On the bottom left is a photograph of our melamine sample again. On the bottom right is the illustration of the double degree of freedom perforated over honeycomb liner. And above the melamine photo is a photo from a microscope, enlarging these tiny, tiny pores of the melamine. So like, what's going on here? It's interesting that these two very different porous liners seem to perform so well in acoustic tests in this apparatus, even though they look very different. When we compare the baseline data to the natural reeds and the synthetic Bioinspired broadband acoustic absorber, we can see that the natural reeds are doing something different below 1,000 hertz. The plastic prototypes also absorb more sound than the baseline liners below 1,000 hertz. And above 1,000 hertz, the synthetic reeds have an absorption coefficient greater than 0.6. So not quite as good as the baselines in that frequency range, but not bad either. And it's certainly not bad for a first try. And we think that we can exploit this difference, especially in the age of additive manufacturing, for a useful purpose. The tested frequency range was 400 to 3,000 hertz. All samples were a 2-inch by 2-inch square cross section, and most were 2 inches deep, although we did test bioliners from 1 inch to 6 inches deep too. With these intriguing results, the NASA research team is asking, how might we create thin and lightweight structures that can absorb broadband noise, that's noise over a wide frequency range, especially below 1,000 hertz, while also surviving the harsh operational conditions such as exposure to sprays of liquid and solid debris and high temperatures. And in this picture, we've placed our little 3D printed prototype in the inlet of the NASA Glenn DGen 380. It's an aero propulsion research turbofan. It's a small engine we have for research purposes at NASA Glenn. But, why stop there? We're asking even more ambitious questions. Like, instead of just absorbing sounds, we're wondering how might we create thin and lightweight multifunctional structures that can absorb a lot of sound, but also be capable of maybe transferring heat or carrying a load or maybe some other function you need, while still being durable enough to survive inside an engine. New materials and structures will definitely be needed to enable electric and hybrid electric flight that we're imagining might be part of the future air transportation system and help us reach our ambitious goals. The Bioinspired broadband acoustic absorber is not the only liner concept NASA is testing. There's many others, and this is just one example. This is a photo of an aircraft engine experiment performed in NASA Glenn's dome. In this experiment, the performance of foam metals as structures that could absorb sound and perhaps carry a load were measured. I want to reiterate that sound waves in these prototypes go in between the spaces between the reeds. Some of us are so used to looking at preferred over honeycomb that it's almost a reflex to think that the sample is oriented so the sound is impinging on the open ends, but that's not necessarily the case for us. For aircraft engine noise reduction, NASA has a variety of research underway related to the bio-inspired acoustic absorption. We're trying to develop physics-based equations of the acoustic, mechanical, and thermal performance of these structures so that we can optimize them for different applications. We're performing more tests, making more measurements, and trying to compare those measurements to the values we calculate in these physics-based models. We're also trying to develop software to help design these prototypes. If you were to do your best impression of Isaac Newton at this point and try to come up with some equation for the acoustic absorption coefficient, what variables would you include in your equation? Would it be length, width, depth, frequency? I don't know. There are so many choices, basically. In addition to the rectangular prototypes I've shown you so far, we have tested prototypes with and without perforate face sheets. Perforate face sheets are often used in application where the absorber is exposed to an airflow. Again, we're mostly thinking about engines. We've also designed some annular prototypes with and without perforate face sheets. The annular prototype on this slide was sized to fit the DGen engine, which has about a 13-inch inner diameter. To date, NASA has tested 27 different bioliner prototypes in the normal incidence impedance tubes. In the graph at the right, I tried to compare the different prototypes to the baselines. I've plotted average acoustic absorption coefficient in two frequency ranges. The overall tested frequency range in blue bars from 500 to 3000 hertz, and the low frequency range in red bars from 500 to 1000 hertz. And as you can see by comparing the trends of the red bars, many bioliner prototypes absorb more sound than the baselines in the low frequency range, 500 to 1000 hertz. Again, a material with an acoustic absorption coefficient equal to 1 is absorbing all sound at that frequency. And a material with an acoustic absorption coefficient equal to 0 does not absorb any sound at all at that frequency. So taller bars in this graph are what we're aiming for. More information about each of these prototypes is available by contacting the NASA Glenn Tech Transfer Office. So if you think this technology has a future on board an aircraft, know that the path is well worn. The acoustics branch at NASA Glenn has been working on aviation noise reduction since the 1940s, and in the process of doing so, we've worked at people at other NASA centers, especially NASA Langley. And we've performed a number of benchtop and ground tests leading up to flight tests for a variety of noise reduction technologies. We did talk about the normal incidence impedance tubes. These are often the first test of a liner. There are also many other rigs and facilities used for acoustic research at NASA. Liners that perform well in impedance tube and flow resistivity rigs go on to be tested in the grazing flow incidence and curved duct rigs. Those are rigs that will allow you to understand a little bit more about how an acoustic absorber performs in the presence of an airflow. Liners that show promise in these rigs can then be tested in the Advanced Noise Control Fan, the DGen 380 Aero Propulsion Research Turbofan, and the 9 by 15 foot low-speed wind tunnel. And from there, the most promising liners go to full-size engine ground tests and eventually flight tests. No single test will tell us everything we want to know, and many more tests besides the one I've shown here will need to be performed before any liner can go from a back of the envelope concept to a part in service. I can explain these rigs and facilities a little bit more. I just really wish we were all on site together and I'd give you a really great actual tour. NASA Glenn does have expertise in materials and structures development for extreme environments, and that's why having a normal incidence impedance tube at NASA Glenn makes a whole lot of sense. New materials and structures that show promise as acoustic absorbers at NASA Glenn do go on for further testing at NASA Langley. The normal incidence tube is just one of the rigs at the NASA Langley Liner Test Facility. Other rigs there include the grazing flow incidence tube, a curved duct rig, and a railometer, the flow resistivity rig. Several acoustic test rigs are also housed in the NASA Glenn Aero Acoustic Propulsion Laboratory, and I really wish I could give you a tour. It's an impressive place to be. It's a large hemispherical anechoic chamber, so no echoes, and it serves dual purposes. It prevents our neighbors from hearing our loud tests, and it improves our data quality by blocking the outside noises from the dome from interfering with our measurements. Inside the dome, there are several test rigs, like the small hot jet acoustic rig, the SHAR, the nozzle acoustic test rig, NACR, the DGen 380 Aero Propulsion Research Turbofan, the DART. We value the dome a lot because it's a spacious, reconfigurable anechoic facility, and it's useful for supporting aircraft engine component and small aircraft engine acoustic tests. The Advanced Noise Control Fan is a large, low-speed fan valued for its modularity too, and it's useful for testing new liner prototypes. It was installed in the NASA Glenn Aero Acoustic Propulsion Lab, the dome, and it was used for fan and liner acoustic tests for over 20 years there. It's currently on loan to the University of Notre Dame, and it's being used by students, faculty, industry, and government researchers to do the same. Noise reduction concepts that show promising results in the ANCF are also considered for more realistic tests in wind tunnels, engine ground tests, and flight tests. We moved the ANCF out of the dome to make room for the DGen 380 turbofan engine. The DGen 380 is a small turbofan engine manufactured by Preece Induction. We're using it as a reconfigurable test bed for aircraft engine noise reduction research. The DGen 380 was used recently to test the multi-degree of freedom liner, one of the perforated over honeycomb style liners with some added features to help improve the acoustic absorption. The illustration in the middle of the slide shows the orange liner spool piece that holds an experimental liner. It's installed downstream of the gray inlet on the left of the illustration and upstream of the existing fan spool, also shown in gray on the right of the illustration. The photograph on the slide shows the actual tested parts. In the photo, the liner spool extension is shown in white. The spherical structure shown in the photo, but not in the illustration, is the inflow control device, and that's made out of honeycomb, and it's used to protect the fan from, ingesting debris, and it's also used to condition the flow through the engine during the ground tests. The way we've installed the DGen 380 in the dome does not allow us to simulate an engine in flight. We simulate engines in flight in our wind tunnels. NASA Glenn has been studying aircraft engines since the 1940s, and while the tunnel was created in the late 40s, acoustic treatment was not added until the 1970s. We can test scale models of aircraft engine fans and small aircraft engines with and without acoustic liners in the 9 by 15 foot wind tunnel. The 9 by 15 foot wind tunnel simulates conditions at takeoff and landing, Mach 0.2, where we're most concerned about aircraft engine noise, since that's when the airplane is operating close to people. Shown here is the acoustic treatment and high-speed aircraft fan model used in the tunnel right before major renovations were made. to reduce the background noise level of the tunnel and to improve the quality of the data that we collect. So the acoustic treatment in the tunnel is shown in yellow in this photo. So many improvements were made to the tunnel during the recent renovations, including upgrading the acoustic treatment on the walls of the test section. So you see them in gray here. We also installed acoustically treated turning vanes and a diffuser, installed serpentine baffles in the tunnel, and a new microphone traversing system. This is a photo from a very recent test of the advanced ducted propulsor. It's a fan model in the refurbished 9 by 15 foot low-speed wind tunnel. The ADP can be used to test new liner prototypes, such as the BioLiner. In addition to these rigs, we were able to work safely in the lab during this pandemic. I was fortunate to be part of a team that designed and built a small fan aeroacoustic test rig. We're using it to test prototypes of small fans that might be used for atmospheric revitalization and life support systems on future long-duration space exploration missions or space stations. Astronauts need clean air to breathe, and fans are needed to move that air around in microgravity environments. This is a test rig that we can use to test multifunctional acoustic liners too. These tests were performed in the NASA Glenn Acoustical Testing Laboratory, which is another reconfigurable anechoic chamber we have at NASA Glenn, another room without echoes. The duct shown in this photo is small, about 3 or 4 inches in diameter, which really helps if you're into prototyping new bioliners like we are. So here's a few close-up photos from that experiment. On the left is a photograph of the small spacecraft cabin vent fan that we tested in 2021. In the center is the 72-channel induct microphone array that was installed upstream of the fan in the duct rig. I've placed a sample of the bioliner on top of the microphone array just to suggest an approximate location for a liner in this test. That it would actually go in between the fan and the array. So if you're interested in learning more, we keep writing articles and giving presentations about our research. Copies are available of these publications just a click away on the internet. I've listed 3 of our recent reports here. The first is a journal article that's been published in the International Journal of Aeroacoustics. And so if you have a subscription, it's readily available to you, or you can get it online or ask your librarian for some help. The second report is available free from the NASA Technical Report Server. It's entitled A Summary of Normal Incidence Tube Tests of NASA's Bioinspired Broadband Acoustic Absorber. And the third is the patent itself. We also have a number of presentations that you might find helpful, especially like if you're just beginning to become familiar with this technology. I've done my best to try and explain what we're doing in simple terms for a broad audience and use pictures as best as I can. I was recently at Bioscene 2022, which was a workshop held at the Ohio Aerospace Institute in May. This year's theme was right up our alley. It was biomimicry and the transformation of transportation. My slides are from that workshop are on the NASA Technical Report Server as well. I also often present at the NASA Acoustics Technical Working Group meetings. That's a series of meetings that's held twice a year. If it's held in person, it alternates between NASA Glenn and NASA Langley, though lately it's been virtual or hybrid, which actually helps us reach a broader audience. Copies of my presentations are from that, the TWG are also on the NASA Technical Report Server, ntrs.nasa.gov. If you're an educator in the audience or a student, you could do a web search for any of these titles and find resources that you can use to teach and learn. You should be able to easily find our video interview from the Exploration Nature Knows Best series, which was filmed in the NASA Aeroacoustic Propulsion Laboratory. NASA also has been offering a high school capstone project that's been popular with AP Physics classes. Ours is called the Acoustic Damping Project, and it's been one of the most popular projects since 2017. So kudos and thanks to the teams at NASA Glenn for supporting that. Also, there's a leveled reader series that's produced by NASA's Aeronautics Research Mission Directorate. It's a series of biographies that describe NASA aeronautics research, including the Bioinspired acoustic absorber and aerospace careers for people who are learning how to read English. So in a nutshell, here's my executive summary for this webinar. NASA doesn't patent everything. NASA does patent technologies that might have a broad commercial potential. And this is just one example. NASA has been motivated to reduce aircraft engine noise pollution, and we've invented a bio-inspired broadband acoustic absorber. There is a patent for this technology, and we are trying to develop it into multifunctional structures that could not only absorb sound, but might also transfer heat or carry a load or any number of the other functions you like. The technology might be especially useful if you're trying to control noise, especially low frequency noise, where the structure is exposed to harsh operating conditions. Maybe there's a spray of water, oil, debris, or high temperatures. Again, we had airplane engines in mind when we invented this, so you can imagine the kind of conditions near the engine during takeoff, landing, and cruise. A growing number of experiments have been performed that have demonstrated that synthetic structures that more or less resemble bundles of natural reeds offer some increase in the sound absorption at frequencies below 1,000 hertz as compared to state-of-the-art commercial sound absorbers of similar thicknesses, weights, and volumes. And we know that technology for and experience developed for aviation noise reduction can also have spin-off uses, not only for space exploration, but for the rest of us here on Earth in architectural, industrial, automotive, and marine noise control applications. And so if you're one of the folks out there who's interested in finding out more, please reach out to us, especially our researchers in the NASA Glenn Technology Transfer Office. We'd love to share more with you. So in conclusion, I want to acknowledge our growing team. I'm so grateful to represent so many people who worked so hard on this. For the help of the co-inventors, Chris Miller, Pete Bonacuse, Chris Johnston, Maria Kozmarski, and Mike Jones. And for all the others who have joined us along this journey, like Ed Envia, Jeff Severino, Jonathan Goodman, Brian Howerton, and Martha Brown, and that's just to name a few. Funding for this work has generously been provided by NASA's Advanced Air Transport Technology Project, the AATT project, which is led for us by Jim Heidman, Jess Reiner, and Cliff Brown. And we've also received support from the T2X and the T2U programs managed by our technology transfer team, Christy Funk at NASA headquarters and Jeannie King here at NASA Glenn. Finally, I want to thank you for spending some time with us this afternoon. I'm going to turn it over to Renee and then answer your questions soon.